I'm gonna draw the censorship.
I get a kick out of how professional these YouTube videos are. Well edited. Nicely done.
If you put yourself in the credit as much as Quentin Tarantino,
Writer.
writer, director, actor.
Well, he does appear in all the movies, right?
Yeah.
Kind of like Alfred Hitchcock, famous for doing. All right. So there is one more problem I'd like to do that's on circular motion, and that's a jet fighter one. We'll just do review, okay?
Okay.
And I'll put up a list of, potential topics that we're going to do. One more problem.
Will Friday be reviewed as well?
Yeah, and then we'll go over those problems that you come up with. Okay. So every group, every group should have a problem that you come up with a solution to. And then we'll go over those like maybe on the document cam on Friday, so you can see what those problems are and their solution. And if you wouldn't mind, a member from, or the group could get together, maybe come up with a brief explanation explaining what the solution is, okay? And we'll just put the solution here, and then you can see it up on the screen. Does that make sense? And then there'll be what, maybe like 10 or 10 groups, and if every group does it, we'll put two of those problems will be on the test. Okay? Make sense? Yeah. And so that'll be helpful, hopefully. And then two problems will be ones I'll come up with, but that's a pretty good deal, I think, on the test. Could potentially know two, but if not every group does it, I can't do that. So, make sense? All right. So, let me do this problem. So a lot of times, if you're dealing with planes, you see like stunt planes or fighter planes, they'll talk about the plane, doing a 9G turn or something like that. And so let's see if we can understand kind of what they mean by that. When you see something like 9G turn on a plane, what that means is that the pilot has a normal force that is 9 mg, okay, on him. What this means is pilot experiences a normal force of 9 mg, where m is the mass of the pilot. And I think for military planes, like 9G is about what they want to do. I've heard stunt pilots doing like 12 Gs, but I mean, apparently it's pretty rough after that. They have inflatable pants, I don't know, that inflate really hard to keep the blood up in your head a little bit, because you'll pass out if it's too much. So let's see how this would work. So let's imagine I have a plane. And it's taking a path and it does a loop in the path, like this, okay? And I'll draw a little pilot as a ball on the seat. So as this plane does this loop, the pilot, this mass has to be undergoing circular motion, doesn't it? So let's go ahead and do a free body diagram. We can do it at a couple of points. So let's do a free body diagram when the pilot is here. I'm just going to draw the ball here. and a free body diagram when it's up here. Let's see which one of those has the highest V force, okay? Say this is moving with a speed V. If you want to put in numbers, do you like numbers?
Yeah.
Yeah.
All right, we'll do numbers. Say it's 200 meters per second is the speed. Let's just call this R for now, and then we'll like maybe the final problem would be something like, what would R be for this to be, for the normal force to be 9 Gs? Let's see, what is R such that max normal force is equal to 9 mg. So that means pilot will probably be able to stay conscious with proper, with the proper gear and breathing techniques and all that stuff. That's a 9. Okay. So let's go ahead and see if we can do this. So I'm just going to call this V for now, and then over here we have V going this way, right? For the sake of simplicity, we won't worry about the changing of the velocity as it goes up the loop. It will change something. When we do energy conservation later, we can figure out what that is. All right, so let's draw a free body diagram for this mass here. What are the forces on the pilot as it goes around?
Gravity.
You have gravity going downwards. Okay. Is that it?
Normal force going
Then
up.
there's a normal force that the seat's pressing up on them. Normal force, okay? Any other ones? I don't think there's any other ones, is there? But, so, at the bottom point here, this is at point, bottom point. The sum of the forces in the y direction is going to be normal force minus mv. That has to equal m/ay. What is the acceleration if this thing's undergoing circular motion?
V squared over R.
Yeah, at this point, the acceleration has to be pointing towards the circle, so in the y direction, towards the center of the circle. And it has to have a magnitude v squared over r. That's the condition for circular motion. So m v squared over r. Okay? So we get a nice equation. We get normal force minus mg is equal to m v squared over r. So let's think about this issue here. We want to find what V, or what this R is, when this is 9 Gs, don't we? It's a little bit more subtle. Let's just check real quick that the maximum normal force is down here, okay? So I'm going to write this as normal force is equal to mg plus m v squared over r. And I added this mg to both sides. Okay. Let's check that the normal force is smaller up here, so that this is a so that this would be a place where we would look for the maximum normal force. Okay. So let's look at the free body diagram at the top. What's the free body diagram at the top going to be?
Normal force and weight force are going down.
Wow, both the normal force and mg are in the same direction, right? And if I sum up forces, I'm gonna have the y direction going downwards here. Just to make equations simpler. If I sum up forces in the y direction, I would then have normal force plus mg. And that would equal m/ay. What does ay have to be? Same thing, because it has to be V squared over R. If I have Y this way, that's towards the center of the circle. So A sub Y is V squared over R. So I get normal force plus mv is m V squared over R. Say I take this, bring it over to this side. I get minus mv then. And you can see that for the same V and R, I get less of a normal force here because this md comes in with a negative sign. Make sense? So it's at the bottom where you'll have the maximum normal force. And you might notice this, like when you go on a roller coaster or something, when you start to go up a hill, you feel pressed down more rather than when you're at the top of the hill. Okay. All right. So this will be where the maximum normal force is. This is the equation for the normal force. And so now I need to figure out what R is when we're at the maximum normal force, 9 mg. So let's go ahead and do that. 9 mg. I'm just going to plug in 9 mg for this end. It's equal to mg plus m v squared over R. I can subtract mg from both sides. So I'd have 8 mg here, right? 8 mg is m v squared over R. What do we notice about the m's?
That's one so.
Yeah, they cancel out because, which is kind of neat. We'll go up to here. So you get that 8, so we can cancel out these m's. 8g is v squared over R. I'm solving for R, right? So I'd get 8gr is v squared, multiplying both sides by R. Now divide both sides by that 8g. I get R is v squared over 8g. If I plug in 200 meters per second, so it's about 2.2 meters per second, or 2.2 miles per hour is 1 meter per second. So about how fast is that? About 440 miles an hour. So it's not unreasonable for a plane. Squared over 8 times 9.8 meters per second squared. And if I do that, what do I get?
510.2.
507 meters. So that means if the plane's going, 440 miles an hour, tries to make a turn, like on one of these fighter planes like this, the circle that it has to go around has to be about 1 kilometer in diameter. So, which is a pretty big circle, just so that they don't die of V forces.
Because if it was tighter than that, the and normal force would be way bigger.
Yeah, let's try it. Let's say that you had a R. Let's go back to this equation here.
And R was
Let's
like
say
twice
R
as
was
big.
100 meters. So football field in radius. So let's say I have N is equal to mg plus m v squared over R. And I'm just going to write this as m times g plus v squared over R. This here would be the G force, right? So in our case, we set that equal to 9. In this case, we're going to solve for it if we plug in 100 meters. So let's do that as m times 9.8 meters per second squared plus 200 meters per second squared over 100 meters. Say what is this? That's all I want. So plug that in so you have 40,000 divided by 100, that'd be 4. This would be,
409.
409.
yeah,
409.8.
409.8. Okay. So I have m times this is so this is some constant times g. I can write it that way, and that constant would be the how many g's you're pulling. So 409.8 meters per second squared is equal to some constant. It's equal to how many g's? Let's call this. This will be a number times g. This is the number of g's that you're pulling, that the acceleration is. And so if I divide this by g, I get what m is. And so what would this be? Does it make any sense what I'm doing here? It's going to be like 40 g's, right?
42.
42.
42 G's. 42. So this normally would be a 42G circle to try and pull that in. Do that in 100 meters. Have a 100-meter radius. Unfortunately, that'd probably kill you. So I think the maximum G forces a person can instantaneously sustain without dying is somewhere around like 40 or 35. They had a guy who did rocket sleds where they tested it. And if you go to the Cosmosphere in Hutchinson, they have the rocket sled there, and they have a little display of this. And he did somewhere around 40 G's, and that's like the limit before you die. Any more than that, and your
Why
internal.
would it kill you?
Why?
Why would you die?
Well, because as you're doing this acceleration, that means all your organs in your body have to accelerate, right? Well, your organs are held in
Gets
place.
squished.
Your organs are held in place by all these little connective tissues and stuff. Those things start to tear, to keep your organs accelerated. And when they all tear up, you probably won't live.
Okay.
So, you know what I mean? Like, if they all go up, it's not good. Yeah. So, yeah. So it's kind of a neat thing. Who's in chemistry? You guys ever dealt with centrifuges?
Yeah.
So sometimes those things can get like G forces of like 100,000 G's. They put test tubes and stuff in a little circle and spin it around at like 10,000 RPM type like circles.
Yeah.
Aren't there human centrifuges? What are they for? Just
There-
to test?
Yeah, there are some at like NASA and stuff. They don't do that. They're not pulling 100,000 G's.
That would be good.
Yeah, that, use centrifuges to separate out, colloidal systems probably. So, like blood, you can
Separate
Separate
out
all.
the different parts.
separate out the plasma from the cells and all that. And you can imagine what your body would do if you were doing that in your body. It probably wouldn't be good. So, yeah.
Is there a unit or a sign we put after 42 for G's?
Nope, because what I did, this is just the number of G's that this acceleration is. Okay. And so this is, this normal force was m times something. I wanted to write that as how many mg's it was. And so that's what I wrote. This n is how many mg's it was. Does that make sense?
Yeah.
Oh, yeah.
All right. So, by the way, for somebody in chemistry, you might want a centrifuge problem is a good test problem. So if you want to do a quick problem like that, that'd be a pretty neat problem to do. Anyway, that's just an idea. You don't have to do it, of course. Don't let me influence you too much. So let's just write up the different problems that we're gonna be doing, that we've done so far, okay? You guys ever seen pictures of what happens when one of those like really fast centrifuges breaks apart? Or you put something that breaks in there? There's some online and stuff that you can see, like the whole labs can get destroyed. Like, there's pretty crazy stuff.
You're talking about a large scale one, right?
Yeah, well, it's a pretty big centrifuge. Well, actually, you know, that's what that the Stuxnet virus did. So one of the ways that you can separate out the various isotopes of uranium is by using a really high-speed centrifuge. Because, you know, the heavier isotopes are a little heavier than others, so their acceleration will be a little bit, well, the force on them will be a little bit more, so, you know, in a centrifuge. And so what you can do is you can use that as a way to try to separate out different isotopes. And so Iran had a big you know, lab where they were doing this type of thing. And there's this worm that was all over the internet. Nobody really knew what it was for, but it was there. And when they turned it on, it messed up those uranium centrifuges and it destroyed the whole lab.
There was a worm inside of it.
It was a computer worm,
Oh.
and that got into controllers of these centrifuges
I don't remember.
somehow. And they used it when they turned it on. They used it to mistime the centrifuge. So that's an example of how the crypto guys, the computer hacker guys, were able to get in there and really mess things up. So nobody took credit for it, but you might guess who's behind that type of thing. So, yeah. Pretty sophisticated. All right. Let's go ahead and go right up to these, what we're going to do on the test. What was the first thing we did? The first thing we did was math review, right?
Yeah.
And in particular, where we did triangles and algebra. That stuff I probably won't test on, but I will test on vectors, potentially. So, you know, vectors, adding vectors, breaking up vectors into components. Angles of vectors and magnitudes of vectors. Angles, magnitudes. I think that'd be about it as far as being able to figure those things out. All right, so this will have all the trigonometry in it, so potentially. So 2.
Kinematics.
We did kinematics next. So this is given a initial velocity and position and knowing a constant acceleration, where is the object going to? Probably the biggest example of this, well, I'll just write the kinematic equations. So we had, this is the y of t, y naught, plus the initial y velocity, plus 1/2 acceleration in the y direction t squared. Same thing with x. If I had projectile motion, this acceleration in the y direction would be negative g if y is going upwards. So we looked at the consequence of this equation for an object that's accelerating under gravity, and that's it. So we did, and then same with the x. Same equation, I just replaced the y with the x. And we looked at, and the biggest example we did of this was projectile motion, the biggest application. And so what we did with the projectile motion was we looked at range of a projectile, height that it gets to, maybe height at a certain time, and spent some time on that. What do we do next?
Forces.
Yeah, Newton's second law. And we also did Newton's third law too, was part of this. And so add up, drawing free body diagrams, adding up the forces, setting that equal to MA, that's what we did. So some of the types of problems we did were, just masses being pushed or pulled on the surface. Masses on an inclined plane. Maybe that had friction in it, so we had to understand the friction force a little bit. And maybe there were multiple masses. We only did really with 2 so far, but
What would like a multiple mass, like, oh,
that's when you pull the person pulls a the mass, 2 masses on a pulley, or a person pulling
oh, right,
sister on
right,
the
okay.
wagon. That was one of the homework problems. So you would just use these types of things to see what's going on. Okay. And depending on the problem, there could be lots of different problems you could have. With this, you might want to know what a force is, knowing the acceleration. So if it's moving at a constant velocity, what's the acceleration? 0. That might be a type of problem. You might want to know what the acceleration is, knowing all the forces. If you knew acceleration and all the forces, maybe you want to figure out mass of an object. So it depends on what the problem is, exactly how you deal with this. But this would be where your starting point probably.
And then whenever we have friction, can you say that?
Yeah.
Go ahead.
So the friction force, that's a good question. Friction force, the magnitude of the friction force is, if it's moving, it's constant. It's called the coefficient of kinetic friction times the magnitude of the normal force. So don't just write friction as mu k. Believe me, on tests, I can't tell you how much I've seen it. This is just I'll give a mass, like 1,000 kilogram mass, say coefficient of friction is 0.1, what's the friction force or something like that, you can just say 0.1. That's a dimension, that's not it. So it'd be
You're
100.
not gonna give us any equations, right?
What's that?
You're not gonna have an equation sheet or anything, right?
No.
No. Just, right.
I'll give a few equations, like F equals ma. I guess I could put this friction on there.
What about the G,
What's
the
that?
2 mass equation with the G constant?
Oh, yes,
And
we
1
did
over
gravity
M.
too,
Yeah.
right? So, force of gravity is G m1 m2 over r squared. That's how big it is. And then the direction would be attractive between the masses.
Will you give us that constant?
And then G, yeah. Yeah, I'd give that to you. You know, I'm not expecting you to memorize it. Yeah, I'd give that to you. Okay? Everyone remember little g is 9.8 meters per second squared? So hopefully you'll remember that. I may remember to give that to you or not. That one gets used so much that you probably remember it. Let's see, what else did we, what was the next thing we did?
Circular motion.
Just circular motion. And so we had to introduce some terminology. So, you know, angular frequency, period, frequency. By the way, this F is different, and, you know, maybe clearly different than that F. So you have to know it from context, right? So frequency, period, angular frequency, relation between angle and arc length. You know, these are just properties of moving in a circle. Some of, you know, is what you need there. And then the biggest thing we did was a mass moving in a circle. Is accelerating because the velocity is changing, right? And is accelerating. And the magnitude of that acceleration is v squared over r, where r is the radius of the circle. That can also be written as omega squared r times r. And the direction of A is towards the center of the circle. And so much of the circular motion is applications of F equals ma, knowing what A is. Okay? So which one of these are you least comfortable with, or are you completely uncomfortable with all of them? Or somewhere in between?
Don't tell him he's
Would we
gonna
be
put
able
that
to-
one on the test.
Would we be able to go through all these in the time we have today and Friday?
Probably not. I mean, there's millions, you can come up, each of these problems probably takes a few minutes.
Probably
Can we do a
kinematics and
projectile
number.
motion problem?
Kinematics and force are
Yeah.
least comfortable.
Yeah, or projectile motion.
Okay, why don't we, do you want to do a projectile motion problem?
Yeah.
Yes.
All right, let's do a projectile motion problem to remind you about, so this is the topic, does at least somebody have it written down that they can share, yeah.
I have it down.
Okay,
Sorry.
sorry. So, okay, so I can erase this, okay? Is that right? All right. Okay, let's try a projectile motion problem. This one we did a lot of projectile motion problems, I think. All right. This one might be good. start out with a regular one. Let's say I have a hill like this, or a cliff, and I fire a cannon with a cliff with an initial speed, V naught is 100 meters per second. Let's say the angle is at 45 degrees. So maybe I want to find out how high does a projectile go above how, let's say this is 100 meters here, so a 300-foot cliff. How high does the projectile get to?
David, did you say the cliff was 100 or 300 meters?
That's 100. 100 meters a second, okay? So, how are you gonna do this?
First we have to do the time, for the time. Solve for the time, right?
Yeah, so if I want to figure out how high above the ground does a projectile get, what time am I looking for?
Time in the air.
Time in the air, I'm interested in the time it takes to go from here to here, if I'm
Uh-huh.
interested in the height that it gets to.
No, when the y,
Max.
component of the y velocity is
Equals
0.
0.
Yeah, so I'm interested in the time to get to this point, right?
Yeah.
And what's the condition to be at its highest point?
V equals 0.
Acceleration.
The total V equals 0?
No.
No.
The acceleration.
In the y direction.
Acceleration in the y direction is a constant, it's G, isn't it?
No,
Yeah.
it's velocity.
It's
Velocity.
Velocity in
Zero.
the y direction is 0, right? When it gets to the highest point, it's no longer going up. It was going up. It was going up, and then suddenly it's not going up anymore. Velocity in the y direction is 0. Now then it starts to go down. So the condition is I want
So we're using
So we're-
velocity in the y direction equal to 0. So the kinematic equations, you need one more equation besides that y one.
Yeah.
You'll need also the relation between velocity and acceleration.
Mhm.
So velocity at a given time is the initial velocity, speed, okay? Or, let's do it in the y direction. Is the initial velocity in that direction? And then what else?
Plus
Acceleration in
acceleration.
that direction times time.
Wouldn't you also have to add the original height?
The constant.
Nope, because if I added a height to that, that'd be adding a height to a meter per second, wouldn't it? A meter to a meter per second. No, this is, we'll be doing that thing when we figure out the position of its height.
Okay.
Here we're just solving for the time when it's at its highest point.
Okay.
So what's AY? If I introduce y direction like that,
G.
what would the A's, what would the acceleration in the y direction be if it's in the air?
G.
G negative 9.8.
Negative G, right?
Mhm.
So. Okay. By the way, G is always 9.8. The sign comes from the direction. Good. And so I'm interested in when the velocity is 0, so what should I put? Where should I put that 0?
The initial, what V naught y?
So I want this to be like that. I want 0 here.
I thought that's the initial.
Yeah, it is an initial y velocity.
The initial y velocity.
Oh, that's not what we're saying. Okay.
We're solving for Vy.
Yeah, we're solving for when Vy is 0, right?
Oh yeah.
So
So
put 0 on
0
this
equals
side.
100.
Okay.
Okay.
All right, and then this would give, I'd be able to get a time from that. One time. What would that time be? So if I bring this over to this side, I get GT is equal to V naught Y, divide through by that time, or by the, not the, divide through by G. Okay, like that. Is that good?
Mm-hmm.
All right. So that's the time when it's at its highest point. If I want to get how far above the ground is it, what should I do?
Oh, you have to
Like
separate the
position.
components. The X and Y components.
Oh, okay. Well, I don't know what V naught Y is, do I? Yet. What would that be? That's the initial velocity in the Y direction.
V naught sine.
You can
Yeah,
figure out
it's
what
V
it
naught
is.
sine 100.
Yeah, with
Right.
the
Sine of
example.
a,
So that'd be this
Sine
part,
45.
that'd be this part of the velocity vector, right?
so would it be V naught
Oh.
sine of 45?
Yep, that's right. Be 100 meters per second. Sine 5 meters. Very good. All right, I have this time now. You know, what should I do with it?
You have to plug it in, Pat.
I have to plug it in somewhere. Where do I plug it into?
With that kinematic equation.
Yeah, I want the quick kinematic equations that are what give me my positions.
Mm-hmm.
So the Y kinematic equation is that Y at any time is equal to the initial Y position
Mm-hmm. Or not.
plus the initial velocity in the Y direction times time plus 1/2 acceleration in the Y direction times time squared. For projectile motion,
Minus.
that becomes minus 1/2 t squared. Okay? So I take this, by the way, what is that? Isn't it like about 70?
70.7.
So 70.7 meters per second, okay. So I know the time now, wait, 70.7
Second.
meters per second. Okay,
Yeah,
so what's the time?
7.22.
So I take that, divide by G, and I get, what is it?
7.22.
7.22 seconds, okay. So this isn't too bad now, because all I gotta do is I gotta plug in numbers. I don't have to solve anything. So what's the initial Y position? That's the height above the ground, right? That starts out at?
100.
That's at 100 meters, if I call this the ground. Okay. So, call that 100 meters. Plus 70.7 meters per second times 7.22 seconds minus 1/2. G is 9.8 meters per second squared times 7.2. You know, the units will work out to meters, so I just have to plug in these numbers. And my result would be in meters. And what would that be? Like 350?
55.
355. Okay.
Are you gonna count significant figures on the test?
No. See, as we're seeing in physics labs, significant figures come from knowing what the uncertainty position, where the uncertainty is. And so I don't want to mess around with them unless it's done properly. And with uncertainty. So whatever goes, you know, if you write out 100 significant, say if you want to write out 100 decimal places, I mean, that's just more work for you.
So in this problem.
Good rule of thumb, though, is to keep significant figures in intermediate calculations and only round at the last step, because if you start rounding right away, you can often mess yourself up by a little bit.
So can you ask us like the range in these problems, right? Or the time or the
Yeah,
initial
I could ask
velocity?
you. Yep. How about the range? How far does it get over to here? What should I do here?
Take the time, yeah.
Let's do that one. Range. Well, we did that a lot though, didn't
Wait
we?
a second. It wouldn't be bad.
What's that?
Did you say?
No, I said first you have to find the time in there.
Yeah, first we have to find the time of the year. Well, that's one way to do it. You could also, I mean, there's a couple ways you can do it. The way I like to do it is figure out the time of the year. Because that's the way it seems to always work. So how would you figure out the time in the year?
With the y equation.
So,
Mhm.
You can do y at any time is the initial y position plus the initial velocity in the y direction minus 1/2 dt squared. Set this equal to 0,
Mhm.
and that's when you can solve this for t. Quadratic equation, it's pretty ugly, but I like doing that. I don't mind it.
so you said final y equals to 0.
Because that's when it hits the ground. Yeah, we're interested in the time when it hits the ground.
Initial y. Okay.
Now, a common mistake is to be, well, we figured out the time to the highest point. Let's just multiply that by 2.
No,
See how that wouldn't work?
because it's gonna be longer.
But can we do it
Second
that
half of
way?
the-
Or, but you can do the 355 meters times acceleration to the ground, figure out that way, right? Or is it something like that?
Well, that'd be like meters squared
Yeah.
per second squared.
Hold on, I forget.
I don't know, I don't like doing it that way.
Yeah, so you couldn't, I mean, if you like took this time and multiplied by 2, that wouldn't work because, you know, that would be, you know, if
From the
it started
ground.
out here, it probably wouldn't work.
Yeah.
But it doesn't start out here. You know, it starts out here.
You can do it just over 15 times 2 and then add the time it takes to fall from 100 meters to the ground.
Well, except that we don't know that time, we don't know the time it takes to go from here to here because it had an initial velocity of 100 meters a second, right?
So then you just
This
use
is
quadratic
on the
equation for that.
downside, as you're coming down. The time is gonna be 100 meters above the ground without.
Well, except for the fact that it has a speed down here, right? It has an initial velocity plus an acceleration. Yeah.
So if we were to go do the quadratic equation, what do we do?
So then you do a quadratic.
Yeah, we do a quadratic
Yeah, can we
equation.
just do that?
All right. So t negative e naught y vector plus or minus the square root of squared minus 4 times this times this thing plus. Okay. All over 2 times this thing, which is negative b. I'm interested in the positive time. I actually take the negative sign here. And then I can make everything positive in there.
Multiply by -1.
Yep, by multiplying top and bottom by -1. And that would be the time it would take to hit the ground. And then what would I do?
And plug it in back into the x equation.
We'll take the initial x position plus initial velocity in the x direction times time. You can set that to 0. And then set this to range. So your range is v naught x times time, which is v naught cosine 45 degrees times whatever the time is. Let's look at it. All right, we'll do your problems in groups and also some Newton's second law next time, okay? On Friday.